Welcome to Maths with EJD. In the previous video, we talked about introduction to differential equations, and where we saw that, of course, I think I made reference to the fact that an equation tells us about a mathematical expression. Okay, you have a mathematical expression to be equal to another another expression, maybe another uh, expression or value or anything like that. Okay. So when you say something like ax squared plus bx plus c equals 5, this will be an equation. Then on the other hand, right, if we talk about differential, so the idea of differential equation, okay, we said that that involves derivatives. So involves derivatives. We said that too, it involves derivatives. So if you have, so we already know in an equation, something must be equal to something. So if you have something like dy dx, okay, minus y equals 0, that's a different, so this is a derivative, then you have an equality sign. So that's a differential equation. So we went ahead to look at other aspects. So in this case, our focus is going to be on some uh, terminology and basic classification of differential equations. That's why this is here. So the first thing we'll be talking about is the order of a differential equation. So the order of a differential equation. So question, what is the order of a differential equation? So the highest derivative, the highest derivative, the highest derivative present, okay, determines the order of a differential equation. Okay. So for example, let's look at the following and talk about the orders, right? So imagine you have the cube y, the x cube plus 2 the squared y, the x squared minus y equals 0. So here, the highest derivative is third derivative. So here we have order 3 because the highest derivative is of the third order. So we have order 3. So imagine this now that you have say you have partial squared u partial x squared plus say um partial squared u partial y squared, okay, and that is equal to 7 for whatever reason. So of course you see here this is order 0 because there's no derivative. This is order 2. If we had the y dx, that would be order 1. This is order 3. So the highest order there is 3. But when we come here, this is order 2, second derivative, though it is partial, the answer here would be order 2. Okay, this is order 2. So this is definitely order 2. So the highest derivative determines the order. All right. So I guess that suffices. Maybe I should just stretch it a bit more and talk about uh the possibility of this one I've been talking about since d squared y dx squared minus y equals 0. So this is zeroth order. This is no. I don't want this is not what I intended to do. Maybe, I mean, if I could do this, I could just say y prime minus y equals 0. Okay, this is order 0 because it has no power. This is 1. So the order here is simply 1. So this is differential equation of order 1. So just if you're looking for the order of a differential equation, look at the highest derivative and that tells you the order. Okay, so let's move ahead and talk about the degree. Degree. So you have order, you have degree. Degree of a differential equation. Degree of a differential equation. So for the degree of a differential equation, right, what should you be looking out for? So here, the exponent of the highest order, the exponent of the highest order, the degree of the highest order derivative, okay? And when it is actually free, when free of radicals of fractions. So if you don't have it raised to power minus something or a fraction, then you can quickly easily talk about the degree. But this day we talk about fractional derivative. So in a fractional derivative, it's difficult to talk about the degree. So if you are talking about whole numbers, then you can easily get the order. I mean the degree of a differential equation. So imagine this now. Okay, again, let's talk about the examples. So imagine example one, you have the squared y, the x squared raised to power 3 plus y equals 0. So first of all, this is, of course, since we talked about order before, the highest derivative here is this derivative here, that's power 2. The second derivative, that's order 2. And the degree, because the highest derivative has power 3, then the degree is 3. Okay, that's first example. What if I do another example? Say this, I have, okay, say I have dy dx, okay, plus x minus y equals 0. Okay, so, and then maybe I now say this is raised to power 2. So the squared y dx squared is not the same thing as the y dx raised to power 2, right? So if you look at this now, the highest order here is order 1, dy dx. So the order is 1. And because the highest order has power 2, so we say that is order 2. Okay? So I mean, so that you won't think that if the order is 2, the degree is automatically 3. Let me do another example. So imagine this now. Imagine this situation where we have 3, we have d squared y dx squared plus dy dx raised to power 4 plus y equals x, for instance. So first of all, the order is determined by the highest derivative. So the highest derivative here is d squared y dx squared. So it is of order 2, okay? But what about the degree? The highest derivative is raised to power 1. In fact, it has no power, right? Because it has power 1, it has power like, but it's 1. So don't be deceived to think that the order of this thing, the degree of this thing is 4, right? So this 4 is on top of is not on top of the highest derivative. So this is of order 2 degree 1, okay? Because the highest order is 2, but it is raised to power 1. It's not raised to power anything more than 1. So this is order 2 degree 1. So pay attention to that difference. So order is determined by the highest derivative present, whereas degree is the exponent, the power of the highest order derivative when free of radicals or fractions. So when there are fractions, it's difficult to talk about the order, right? So that's really important. So everything we've been doing so far, you can look at them as some terminology, right? So we've talked about some terminology, terminology, okay? Terminology of differential equations. So let's talk about basic classification. Now that's the other part of this basic classification. So, we talked about types of differential equation in the first video where we saw ordinary and partial differential equations as the two types. But here I want to see some classifications, and they are quite interesting. So the first thing, let's talk about, we can classify differential equations as linear or non-linear. So differential equations can be linear or non-linear DEs, okay? Linear or non-linear DEs. So when do you say a differential equation is linear, right? When do you say differential equation is linear? So in the case of linear, the dependent variable, dependent variable and its derivatives appear linearly, okay? And appearing linearly means that they have power 1, not more than 1. Pay attention that it is dependent variable and the derivatives of that dependent variable, because it can be really confusing. So let's look at some examples to drive the point home. So I'll give possible scenarios to make it clear. So imagine here you have y prime prime plus xy prime plus y equals 0. This is linear for sure. It's linear because y prime, the dependent variable is y. So you have y, we have y prime, we have y prime prime. So the y itself and the derivative of y are all, they don't have any power more than 1, okay? So they are basically linear. And y itself is not, y is not like y squared. So look at this now. If you have number 2, and we now say, if you say y prime prime plus x y prime prime plus x squared y prime plus y equals 0. This is still linear, right? Because although x is now the independent variable and it is raised to power 2. X is non-linear, but we don't care. It is still linear in this case. The differential equation is still linear because the dependent variable y and its derivatives still are linear, though the independent variable is non-linear. So be sure to get that correctly. Okay, so let's go ahead and talk about non-linear. Non-linear. So when do you have non-linear D's? Non-linear differential equations. Non-linear differential equations. So here we've talked about linear differential equations. Okay. Now let's talk about that. So the non-linear differential equation, they actually contain non-linear terms. They contain non-linear terms of the dependent, be careful, not independent, of the dependent variable, of the dependent variable, whatever that is. It does not always have to be y. In case you have the x, the dependent variable is x in that case, so be careful. So contain nonlinear terms of the dependent variable or its derivatives. So if you have nonlinear terms of the dependent variable or its derivatives, so you say you have a nonlinear differential equation. So let's look at some examples. Examples now. You have again, number one, you have y prime prime plus y times y prime squared. So first of all, right, and this is equal to 0. First of all, y prime raised to power 2 makes it non-linear. Then second of all, y times y prime prime is also non-linear. So this is non-linear at two levels. The fact that y prime is raised to power 2 and the fact that even if y prime was not raised to power 2, the fact that y prime is multiplied by y again, it's non-linear. So this is actually non-linear. Very important to pay attention to that. So imagine this again. You have y prime prime plus y prime equals 0. This is still non-linear, though y prime does not have power 2 anymore, but it is still non-linear because you have the derivative multiplied by the dependent variable, the derivative of the dependent variable multiplied by the dependent variable. It is still non-linear. So imagine again, you have 3 y prime prime plus y squared, right? Plus y squared equals 0. This is still non-linear. And what makes it non-linear is the fact that the dependent variable is raised to power 2. This is what makes this non-linear in this situation, okay? So these are all non-linear, okay? So we have seen the first categorization, classification, talking about linear versus non-linear Ds. Now let's go ahead and talk about um, another set. That's initial value problems, initial value problems, initial value problems. That's IVPs versus boundary value problems versus boundary value problems, BVPs. Okay, so how do we talk about this? So first of all, let's talk about IVPs. Under numerical analysis, we talked about methods for solving IVPs and BVPs. Okay. So for IVPs, I think that was where we saw Euler method and Runge-Kutta method. And we went to boundary value problems where we talk about shooting method and finite difference, finite elements, and the rest of them. Okay. So I may still have to refer to that when we come to method of solution. So talking about initial value problems, right? So given given initial conditions, given initial conditions at a single point. So when you have initial condition at a single point, okay, you have initial value problems. So for initial value problems, you have initial conditions given at a single point. So a very good example would be this. So you have okay, say you have one y prime plus y prime plus y, okay, equals 3x. And then we now have y of 0 is equal to 2. So in this case now, you have initial condition given that you have only one condition given. So that's an initial value problem. So another example of this is maybe you have this squared y dx squared plus y squared equals y, if you like. And then you still have okay. Okay. I mean, you can only have initial value problem for first order, I think, because for second order you need more than you probably need more than one or something like that. Yeah. So let's say you have y prime, okay, or let's say you have let me even go something else. Let me say you have dx dt. So now the dependent variable is x. Dx dt plus x squared is equal to 2. And then you now have x of 1 is equal to minus 2, or x of 1 is equal to minus 1. Whatever, I'm just doing this. All right. So this is an initial value problem. So let's talk about boundary value problems. So the idea of boundary tells you it's not just one point this time around. So you have BVPs. So in BVPs, conditions, the initial conditions are specific. This conditions actually not, it doesn't have to be initial now. So probably you have an initial condition and a terminal condition, if you like. So conditions are specified at different points. So when you have conditions specified at different points, it may not even be terminal at different points. So it can be initial condition and middle condition or whatever. So a very good example would be first, say um you have y prime prime, you have y prime prime plus y equals 0, and then you have condition y of 0 equals 1. That's one condition. And you have y of pi equals 0. So that these are, you have two conditions here. Here, don't forget, here you have just one condition, right? This is another one condition. But here you have two conditions. So you can even have more than two. So that'll be boundary value. So imagine two, I have the the squared x dt squared plus dx dt plus x equals 2. Okay. And then you now have x of 1, x of 1 equals 2. And then you now have, say, x of 7 equals 4. Okay. If you have this, or in fact, it might even be x prime of 7 equals 4. You can also have this. So this is also, you have two conditions, and this one involves derivative. So this is actually a boundary value problem. Okay. Having said that, yeah, I think these are like some key categorizations or classifications of these things. Now, can we switch over and talk about uh, methods of solution? Methods of solution. All right. Okay. So solution methods for differential equations. Solution methods for differential equations. Okay, in talking about numerical analysis, we've taken care of some of this, so I'm just going to be referring you to them. So imagine, okay, first of all, we have what we call, we generally we can talk about what we call analytical methods. Analytical methods. Okay. Analytical methods. Okay. So these analytical methods, they are mostly closed form methods. Closed form methods. Okay. When you solve a differential equation, right? You're looking for the function. Your solution will be a function. When you solve a function, you're looking for variable, right? So what I mean is, if you have y squared plus y minus 4 equals 0, when you solve this, right, you're going to get specific values for y. Okay, for y, maybe y is equal to something something. That is that, right? On the other hand, right, if you solve y prime prime plus y prime equals 4, okay? If you solve this, you know what you're looking for? You're looking for y, which is a function of x. So you're going to get an expression. Here, you're going to get a number. So this is going to be a number, right? This would be a number, a value. Okay, and this is going to be like an expression, say y squared plus maybe y plus 4x or something. This is going to be an expression. Okay, that's the difference. So solve an equation, you get the value of the variable, but solve a differential equation, you get the expression. You get an expression. Okay, so they are mostly closed form. Okay, should I say methods? They are mostly they let me put it better. Analytical methods mostly they they mostly give, I think it's better. So they mostly give closed form solutions, closed form solutions. So it means when you solve the problem, you're going to get y is equal to something, something for sure. Okay. But the other, okay, under this now, we can begin to itemize possible methods, right? So I can say they include, I mean, analytical methods include, uh, say, separation of variables, separation of variables. Okay. Separation of variables. I think that's the first thing we're going to see after this video. So separation of variables. In this case now, um, just like as the name implies, you group variables, similar variables together. So imagine f of y dy equals g of x dx. So you put x with x and you put y with y, right? Like dependent variable goes to dependent variable, independent variable goes to independent variable. Wherever you find them, you put them together, and that's the way to progress with the solution. So the separation of variables is one way. Another way, which is still analytical, is the idea of integrating factor, which you're going to see very soon. Integrating factor. So all these are under analytical solutions. Okay, integrating factor. So and they work for linear, they work for linear first order, work for linear first order differential equations like y prime plus p of x of y equals q of x. So any set of equation you can write like this. You know, you can use separation, you can use integrating factor for them as far as you can regroup it and it comes out this way. Then we also have the idea of characteristic equation, which is also a a closed form method, an analytical method. So you have characteristic equation. Okay. So you solve a characteristic equation, you get eigenvalues or something like that. So here they are used in linear differential equations with constant coefficients, with constant coefficients. Okay. So you have characteristic equation solution. Also, you have what you can call the Laplace transform. If I were going to see the Laplace transform, when I get there, I'm going to probably create a different playlist and then join it together with numeric with the general playlist on differential equations. So Laplace transforms. This one actually convert differential equations into algebraic equations. So if you want to convert differential equations into algebraic equations, and once you can put them into algebraic form, then you can solve. Okay. And there's also Laplace inverse Laplace transform. So that way you can change the algebraic equations back to differential equations. So watch out, we are going to talk about this. So having talked about analytical methods, right there, we also have numerical methods for solving differential equations. So we have numerical methods. Okay. Here, and thankfully I've dealt with them under numerical analysis. So these are useful. These are useful when when analytical methods are difficult, when analytical methods are difficult or impossible. So there are situations where analytical methods are difficult or they are totally impossible. So in that case, we use numerical methods. Um, they include, thankfully, I've dealt with this a lot. So they include um, Euler's method, Euler's method. So you use Euler's method for initial value problems. Euler's method used for initial value problems. Why am I repeating the same thing? Yeah, Euler's method. Then you also have Runge-Kutta method. Runge-Kutta method. In fact, it's a group of methods, right? But the fourth order is the most common. Okay, so this actually go for initial value problems. So we still have other numerical methods like finite difference method, where you discretize the differential equation. So finite difference method. You also have a finite element method, still on discretization, finite element method. And lastly, I mean, there are so many more. So you can have a shooting method. Uh, so I think this involves you transforming the different a second order differential equation into maybe two first order differential equations and then solving. So this work for boundary value problems. So these are numerical methods. Okay. So with this, we come to the end of this second video on differential equations, where we talk about terminology and basic classification of differential equations. All right. So if you have not subscribed, please go ahead and do that right away and hit the notification bell so you can always get alerted each time a new video is released. Because after now, we'll start solving some problems. We'll start taking it from the very small level, like separation of variables, and things get to escalate. So just follow step by step so you can follow through. So subscribe and hit the notification bell so you can always get alerted each time a new video is released. And if you have subscribed, thank you so much. Then in the comment, let me know how helpful these videos are for you. Let me also know if there's a topic you'd like me to solve or a topic you'd like to treat, a problem you'd like me to solve. And hit the notification, like and share so that more people can have access to this great content. So in the next video, watch out for separation of variables where we begin to tackle problems like that. All right. Keep doing math right till I come your way again. Bye.